Today we are basking in the glory of the summer sun, enjoying the light from the sun, right? 1 kilowatt per square meter plus a little added humidity for free. Okay. Is the sun a source of energy? Yes, right? Does the sun provide power to us? Yes. How much does it provide? And in what manner is that energy stored and then released? So the sun is acting by a process known as fusion, the fusing of small things together, right? And that causes some energy to be given off. The light that we are getting is given off by electromagnetic radiation. Electromagnetic radiation, something we're getting towards now. The photons are in the visible that we see. We get them in ultraviolet, we get them in infrared, and that warms our souls. Okay, so the sun is a way to store energy. What's another way to store energy? Batteries, right? Okay, so batteries, the old galvanic cells, those things work okay too. Another way to store energy chemically, right? Petroleum. All those lovely hydrocarbons per cubic centimeter providing so much possibility. Another one is just to do it directly with electrical processes, to push charges onto electrical conducting plates and then hold the charges there and bring them back when we want them to do something later. So we developed the concept last lecture of the ability to store charge. The ability to store charge, and now I want to add that when we store that charge, we are also storing energy that we have that has the potential to do work. If it has the potential to do work, what kind of energy do we think of? Potential energy. The words help drive the thoughts. So let's go and take a look at putting charge on a capacitor. So if we put, well, let's just do a simple one to start. If we have some kind of place that we want to store a charge, and there is no charge there to start with, so then we bring in an element of charge. So we'll bring some charge from over here, and we bring it over to that piece of metal. There's no charge opposing it. There's nothing electrical in the forces if we're thinking in a simple way. And as a result, putting the first charge on there doesn't take any work to do it, right? Now we have suppose that there is some charge over here. And so how much charge shall we have? Let's have it be Q. And now if I want to bring this charge over, I have to push. If it's the same sign, I have to push and do some work. So as I bring it in, I have to do an element of work. The amount of work I have to do depends on what the voltage is here, as you were suggesting, what the voltage is here. So I have to do an element of work to bring it in, which is bringing in however much charge I want to add to that, and it's going to have to go up the hill, the potential hill. So I have to do an element of work, Q times V, to bring it in. If I want to do a lot of work and bring in consecutively more charge, I'm going to have to do this and add them up. And you go, oh, that's not a hard integral to do. There's a dq there, and there's just a v. And, well, V, that's the voltage, okay. But there's a problem. V depends on the amount of charge that's there. So as we bring in the next element of charge, the amount of charge that's stored on that sphere, as I've drawn it there, or circle, increases. So the voltage increases as Q gets larger. So as we run over the range of Q's, building up more and more through the dQ's added, this guy changes. Well, let's see. Capacitance was the ability to store charge. How much charge per volt can be stored. So that tells me that the voltage that's on that device is equal to Q over C, conceptually. And we remember from last lecture the calculations for capacitance. The capacitance of an object depends only on the geometry, the physical geometry of the material chosen, and what material was there. So the geometry is all that matters for this. If we don't change the geometry, what happens to C? Nothing. C stays constant. So we can bring our calculation for the total work done is going to be integral V dq, integral, this is Q over C dq, and I switched from the conceptual Q in the capacitance definition to the specific charge that is at that point on our capacitor. And we get an integral that's not too tough to do, is it? Okay, so we get 1/2 C times the Q squared, whatever the total, let's put a big Q so that you'll think it's a total charge stored at whatever point. So the energy stored in a capacitor is written that way if we want, or 1/2 C V squared. Yes?
Is it 1 over C?
Excuse me. So a 1/2 CV squared, Q squared over 2C, and you can also get Q and V together in one equation if you want as well. So the energy stored is related to the voltage on the capacitor. The higher the voltage, the square of the voltage. It stores up pretty rapidly. And why would it go as a square instead of just linear is as you build the voltage up, it gets progressively harder to add each additional charge, each incremental charge. It's progressively harder. It's not just the same. So we expect it to go something stronger than a first power in the voltage. And the square is fine. Okay. Now we also observed that the capacitance depended on the material between the stored charges. That is the material between the plates. So we had an example with some cardboard, an example with some plastic, and of course we used air. So for example, right? What does this mean? So remember, you do physics without simplification, right? But I've simplified something here. What is e.g.? For example, right? What does it mean in Latin? Ed, ed, right? Gratis. It is with thanks, it is an example, okay? So it's not a complete thing. Okay, let's just do a, what does that one mean?
In essence.
That's a fair enough way to say it. What's the Latin for it? Id est, that is. It means specifically. It's not an example, it's specifically true. Okay, so let's, we're not doing an id est here. We're doing, the examples we had were air, cardboard, and some kind of plastic. I don't remember what type it was. Okay, when we added these materials, what happened to the capacitance? The capacitance increased. C went up when material was added. When the cardboard replaced the air, right? And the ratio, the capacitance with the cardboard compared to the capacitance in the air was about what? I'm remembering about 1.5. 200 picofarads for the air, 300 picofarads for the cardboard. The ratio of those two was about 1.5. That number, the ratio, is described as the dielectric constant, or called kappa. This ratio is this C, the ratio of those C's. And we may also describe dielectrics by using what we call is the permittivity. I may get this spelled wrong. I don't know if I got that spelled right or not. The permittivity epsilon. So we have epsilon naught for vacuum or free space. And epsilon for dielectrics. So epsilon naught has a value of 8.85, 10 to the minus 12 in the MKS unit systems. And so there's a permittivity of dielectrics, say cardboard, is going to be 1.5 times that. Okay, so what is 1.5 times 8.85, 10 to the minus 12? And your first reaction is, I don't know, right? Something 12, 1.2 times 10 to the 1.3 times 10 to the minus 11. And then, oh, we have to remember for the plastic, it's going to be about double that. Now, do you want to carry around charts that have things at 10 to the minus 12, 10 to the minus 11, all kinds of numbers? Or do you want to count things on your fingers? Counting on the fingers is a lot easier. So what we typically use is kappa, which is the ratio of these two permittivities. So kappa is epsilon over epsilon naught. And we can figure out the stored energy. The stored energy. Well, let's look at the capacitance. Capacitance of parallel plates we had that it was epsilon naught A over D. Now with the dielectric, it just goes to epsilon A over D. Or if you want, and you can see using this kappa or epsilon is very straightforward to put the dielectric material in and do our thing with it. Now, of course, these kinds of descriptions are approximations. And they are valid over some kind of range of conditions that we are considering. The capacitance of the parallel plates only holds the charge until electrical breakdown at a high enough voltage will cause the current to flow between the plates. When you have dielectrics now, the voltages or the electric fields at which breakdowns will occur are different than just free space. So just like if you're using a spring, you want to use a spring for a purpose. For example, the chair you're sitting in has a springiness to the cushion. You would not bring an elephant in and have them sit on this chair, would you? Because you know that the properties of the spring will no longer be reasonably described by the Hooke's law you're thinking of for the human application for it. So when you do anything with these different materials, you have to think about, okay, I've changed the material. How does that affect what's going on? Hopefully a simple picture will work and describe things for you, but you have to always keep in the back of your mind, the world is complicated. So when we do a demonstration up here and it works, it's because people spent a lot of time doing demonstration development that didn't work. All right? This stuff is hard won. It is not easy to get it to this kind of position. So whenever you look at something for stored energy, okay, great. Over what conditions does it apply? Okay? Keep that in mind. Okay, well, let's see. Let's go forward and move some charges now. Okay, moving charges. So this is current events. If we want to make electrical charges move, there are different perspectives you can take to get them. But I guess what I'd like to do is start by putting on my electron hat, okay? And you guys all put on your electron hats also, okay? There, we got quite a few of them going on. You can put on a proton hat if you prefer, it's all right. I picked the electron because the electron is particularly mobile. As an electric charge, it has a very low mass. So it's real easy to move it around. And it's pretty cooperative in that moving in some kinds of materials. So let's think about how we might move some charges. Suppose we have, let's see, how do I do this? So we have some volume. How large would you like that volume to be in your mind conceptually? Aren't there convenient volumes like 1 cubic meter? Isn't it nice when you pick a number that's easy to work with? Okay, like on the quiz, I gave you the separation was 2 10 to the minus 10 meters, not 1, so that the midpoint was 1 10 to the minus 10 from the charges. Makes the calculations easier. Okay, so that's supposed to be like a cube, okay? So this cube is, you might picture it to be 1 cubic meter. How many charges are in it? Right now you see none, right? So let's add some charges. We put some in, and we've got our charges in there, and we have n charges per cubic meter. So this is the number density. It's not the mass density. It's the number density of particles that are charged in there. So we have n charges per cubic meter. And let's imagine that entire cubic meter is all very cooperative. We grab the cubic meter and we just move it all along over here. How fast am I going? About 1 meter a second, right? So I have some speed that I'm carrying those particles. If I wanted to think about suppose we have them all moving at some velocity like that, then the flux of these particles would be n times v and if I wanted to know how many charges I was carrying, I could go n times v times q. If the q is so number density, this is the charge per charge carrier. And this is the charge velocity. That quantity is typically written as J and is called the current density. You can do this kind of conceptual building up of a current in any number of other places. Like on a river. You could take the mass per unit volume if you wanted, or the number of molecules of water per unit volume, multiply it by the speed, the velocity in the river, and get the water flux in the river. And then if you're standing on a bridge, the water goes under the bridge. You may have an interest in the total water passing under the bridge per second. Not just the density of the water flux in 1 cubic meter going along, but you may want to know the total. So if you knew this quantity and you knew the area of the river flow, where the water flowed through, the area through which it flowed, then you could calculate the total current. For example, if we're breathing, I'm breathing some air in, I'm breathing it out. If I want to know the total air, I might want to know the air flux times if I'm breathing through the mouth, or if I'm breathing through the nose, the area through the nostrils, right? Same kind of idea, but now we're doing it with charge. So if we want to figure out what the total current flowing under the bridge is, we take the current density and we integrate it over the area we want to look at. So the total current is the integral of the current density over the area through which it flows. And this commonly, that's when J is parallel to dA, goes to I equals integral J dA, and may go to J times A. Yeah? Okay. J has got some direction to it, just like the rain falling from the sky. And when you hold your umbrella, the flux hitting the umbrella depends on the angle of the area of the umbrella compared to the direction of the current density. Same thing here. So if we want to think about a wire carrying current. Suppose we have a wire, and there are charges in it. They're flowing at V. And here is the A we're thinking of, the cut through the wire, right? So the current I is a macroscopic quantity. J is a microscopic quantity. So we think either way. You can have your electron hats on, or you can have the macroscopic picture without the electron hat. Okay, now let's think about moving those electrons around. As I'm walking around up here, do I collide with anything? No, right? Can you come up and be a source of collisions? Okay. So it's Harry?
Yes.
Okay, so Harry is now going to be a source of collisions, okay? I hope it will not present any friction between us, but it's what's going to happen, right? So if I go along now and I hit Harry, what happens to my momentum?
Shifts.
It shifts. He would get, by that particular collision, he would get pushed that way, and I would get pushed this way, wouldn't I? So the directed momentum that I had before the collision got changed. If we have a head-on collision, bam, now I even can get turned around, huh? So depending on how we collide, have a seat, Harry, thanks. Depending on how we collide, the human collider, Harry. Thank you very much. Okay, so depending on how we collide, my momentum gets randomized. I had a directed momentum making current, but it got randomized by the collisions. Now suppose Harry had some brothers. And so there were several of them up here. And then I walk along. I'll have collisions more often, won't I? So the collisionality of the process matters. The frequency of the collisions determines how quickly my directed momentum is lost. So if I start out, if we put our electron hats on, and we have some charge moving this way, and then there are other charges it might go by and collide with, collisions with other charges randomize the initial velocity, right? The momentum in that direction is lost. The momentum is lost in the sense that the directed flow of those charged particles reduces. The momentum was exchanged, given over to Harry's family. As I hit into Harry's family, it causes all of them to have a reaction. They get the momentum, right? So it's not like the momentum goes away. It just goes away from the charge carrier that was trying to be the current. So if momentum is lost from directed charge, right? directed flow by collisions the frequency of those collisions tells us something, doesn't it? If I have the collisions twice as often, then the momentum will be dissipated twice as fast. If the collisions happen 10 times as often, it'll take 1/10 as long. So by collisions, so if it's lost from collisions in a collision time, then we have, let's see, the frequency is, let's see, nu, well, you like F's? Frequency is 1 over tau, right? I want to call it nu because I like that. Okay, what is nu? It's an ungulate found in Africa, right? Just throwing in a little added lagniappe. Okay, so the frequency is 1 over the collision time. The momentum that I had before the collision is m times v. The momentum is lost then at a rate, mv over tau, momentum loss rate. Now let's see, if I think of it that way, that's delta P over delta T, isn't it? The rate of loss of momentum. What does that mean? What's another word for momentum loss rate?
Inertia.
dp dt equals F, force, right? So we have a momentum loss rate, force equals dp dt. And that's equal to, well, what are the forces that are involved here? If I wanted to get the charges moving, what would I do to push them along? I would apply an electric field, right? QE, and then the momentum loss. You could put a, if you want, I don't care if you write it this way or that way is fine, either way. But just be careful to keep your nu and your v understood and separate in the way you do your notation. So the force on the charged particle is whatever electric fields are accelerating it, and then that pushes it to faster speeds, and the momentum loss reduces the speed. That's why I put a minus sign in there. Okay. Suppose equilibrium is reached. I have some electric field getting me going, pushing me through the crowd, and the crowd is opposing the motion, so there's some friction. Suppose equilibrium is reached. So my speed arrives where QE equals mv nu. Let's multiply by n times q, the whole thing. Nothing fancy in that, just multiplying through. I see N times Q times V. So I have N Q squared E is equal to J M nu. Let's do E equals we arrive at that relation, that the electric field is pushing and the frictional loss is reducing, and they balance each other in this way. The electric field, it says, is proportional to the current density, or the current density is proportional to the electric field. Either way. This is called E equals eta J. And this eta is called the resistivity, the ability to resist. If I wanted to write it conversely, that J was equal to this way, then we would call it sigma E, and sigma is conductivity. So we see that sigma and eta are just inverses of each other. Something that conducts really well opposes flow very poorly. Something which opposes flow very well does not conduct very well. You can choose which way you want to talk, resistivity or conductivity. Either of them are suitable. Yes, question?
When you say E squared?
Oh, put a Q here if you want. Okay. It's the charge per charge carrier. And you'll see it written with a Q there. You'll see it written equally often with an E instead. Either way. Okay. And my brain just flipped between because I'm thinking without looking at what I've already written. Okay. So the ability to resist flow then depends on how much friction there is. If we take our hands and just rub them, you create heat. Sometimes that's a good thing, right? And what you're doing is rubbing charges right near each other and changing some of the momentum at a microscopic level into random motion, random wiggling, random oscillations of those charges. That's the heat that you feel. So electrical flow follows this kind of pattern. And we can think about now, let's see, electric field is the force per unit charge. And if we think about voltage, V, voltage was the work per unit charge. So you can think about pushing per unit charge or how much work is done per unit charge. Either way. If we want to think on the macroscopic scale, so this is our microscopic, right? Microscopic. Go now, leave the microscopic. And go macroscopic. Let's live large. So if we have E equals eta J, and we want to go large. So we need to think about the ability to resist flow. So we have some length, some area, and some microscopic property there, we see that the overall ability to resist the flow will go as the resistivity, the frictional properties of the material, times the length over the area. The longer the path through the material, the bigger Harry's family is, the more people I have to push through, the bigger the total resistance. On the other hand, if we can spread them out to a larger area, that can make the flow easier. How many of you have used a straw to drink something? A straw, a simple straw. Are there any here? Does anybody have one? Do you have a straw handy, anybody? Okay, here's a straw with chalk on it now. The straw has a length to it, doesn't it? And a surface area. And I could make little spit wads and shoot them through there, right? The surface area is, on this straw, what? This is a small one. It's about 4 millimeters in diameter, maybe 3. How long is it? 10 inches, 15 to 20 centimeters, somewhere in this range, right? If you made the straw bigger in diameter so that it wasn't so small, would it be easier to suck a liquid through it? Yeah, it would be, right? And so this is a fairly small straw, small diameter. If I was going to have a malt or a shake, would I want to use this straw to drink it? Not if I wanted to consume at a rapid pace, right? Because when you start to go and trying to make the pressure differential as much as you can to push the stuff up from the malt into your mouth, this thing is going to oppose the flow a lot because area is small. If we make the area larger, the liquid will flow through here much easier. If we make the straw shorter, it will flow through easier. Shorter straw, less resistance. So this kind of model also works for fluid flow, airflow, liquid flow that you can think of in a lot of circumstances. So the trade-off on straw design then is the material costs 2 pi r times L. The smaller the diameter, the thinner you can make the wall of the material and still have the strength to hold against the pressure differential or the squeezing. So the manufacturer would like to minimize the material used, 2 pi r times the width times the length, minimize that, but still satisfy the function it needs to do. You will see, if you go to different places, different straw designs in play. Maybe they have slightly different resistivities of the liquids they're selling you, right? Or they have one straw for all of them. Maybe they're going a little higher brow and give you a little more material in the straw for your money. You're going to pay a little more. Okay. Never would have thought the straw got so many design elements in it, but it's the same kind of thing that's going on here. The resistance goes as the microscopic ability to resist flow times the length of the resistor divided by its area. And we arrive at, on the macroscopic, V equals IR. The voltage per unit charge is the total current times the resistance. This is called Ohm's law. If you study things that are related to this, you'll discover that Ohm's law has a lot more terms in it than this. V equals IR is a really simple circumstance. Kind of like using Hooke's law for springs. Works well for a lot of circumstances, but not everything. So V equals IR. And you go, oh, that's terrific. For any given voltage, if I know the resistance, I'll get a particular current. And then you go look up the resistance or the resistivity of the material in a chart. in your book probably, I believe your book does have some charts. But those charts are good for specific temperatures, specific material designs at specific temperatures. By the end of this week, you should be able to look at, say, a standard old kind of light bulb. There's a tungsten filament inside. We'll probably break one apart and show it to you. And at room temperature, the resistance of this circuit is very small, less than 1 ohm. The units of resistance R, the big R, are called ohms, OHM. It's not the ohm, right? It's OHM. And you find if you measure this at room temperature, the resistance is less than 1 ohm. But when the light is turned on, the resistance is substantially different from that because the bulb is hot. Oh, the bulb is hot. Let's ask ourselves, do you see the size of this bulb? What's its diameter approximately? 10 centimeters, say. What about this guy over here? Smaller, right? Well, oh, this uses less glass, the smaller one. What stupid person made the bigger one then and wasted money? And you think, well, wait a minute, maybe they weren't stupid. What do you suppose is the difference?
Lumens.
Lumens is one factor, is going to play a role. It's the amount of radiated light, including heat, right, that comes through. Glass, if you warm it up, you can make a pool out of it if you get it warm enough, right? It will make a puddle. Both of these bulbs are designed so that in operation the glass does not puddle up, does not fall down into a pool. This one needs a bigger radius so that the heat can be distributed over and re-radiated over a larger surface area. That keeps the glass below the deformation temperature. This one has a lower wattage, doesn't put out as much heat, can have a smaller glass bulb. If you come into my lab, look at the bulbs that I have up on the ceiling. Their diameters are more like this. Because this guy's like 10, 20 watts maybe. This guy's probably 60 to 100 watts. Oh, this is 150 watts. And the bulbs up on the ceiling in my lab are like a kilowatt, 1,000 watts each. So the glass has to be much bigger for them. The resistivity of the light bulb when it's on is substantially different from when it's sitting there cold where I could hold it in my hand. And by the end of this week, you should be able to tell me what that difference is. You should be able to quantify it by your own means of estimating. Right now, probably not. So if we wanted to find the resistance of the filament in that light bulb, we would go look up in a chart, eta for tungsten. We'd measure how long the filament was and its surface area, or its cross-sectional area, cross-sectional area, and then that would tell us the resistance for the conditions of that chart that we looked it up, okay? And the chart that we look it up typically would not apply for when the bulb is on, so you have to be careful. Charts oftentimes don't put the temperature at which the measurement was made. Okay. Let's make some current flow then. Shall we do that? Oh, let's see, we did over here. Who was the last? Uh-oh. Have you helped already? Have you helped? You wanna? This is great stuff. Hi there.
Sam.
Sam? Roger. Hi. Nice to meet you. Okay, let's, this is called Jacob's ladder. Has a sort of funky name for that. And That's a cute name. What's that say?
Transformer.
Transformer. That's great. Oh my God. So, oh, you know what? It's got to be a French company because half of the stuff on the label's in French, huh?
Mm-hmm.
Okay. All right. What does it say here?
Hazardous voltage.
Keep reading.
Will cause shock, burn, or death.
You do it. Okay, here's what we're going to do. Touch. It was okay. He saw that it was okay because I did it first. And I either have an inordinate ability to withstand pain or it was okay for both of us, right?
Yeah.
And as far as I know, I'm kind of normal in the pain department. Okay, so what is this? Look like wire, right?
Yeah.
Okay, and then there's a thing down here called a transformer. And we haven't got to them yet, but we will. The excitement will continue. What do you notice about the shape of this ceramic stuff here?
It's like a circle.
And
It's like a wave.
yeah, it's got the cross section kind of goes like that, right? As you go along there. And the reason for that is to make high voltages can have electric fields which go along the surfaces of the insulators and could cause an electrical breakdown. And so if you put this shape with the undulations, it reduces the probability, the possibility of a breakdown like that. So we got a wire from one thing that looks like it's high voltage running over to here, and another one coming up here, right? Let's turn it around so it faces those guys, just for fun. And then you're in charge, okay? So this is your switch. This you can turn on and off. Don't touch anything over here, okay?
Okay.
All right, go ahead.
Turn it on.
Yeah, why not? Okay, let's turn that guy. Now get your observations here just a little bit. Yeah. Sam, are you there up there by yourself? Is that right? Okay, so who's the gal in the white that's, sorry, yeah. Yeah. Can you take good notes and give Sam some notes for this demonstration? Okay, that's close to where you're sitting, right? Okay, thanks. All right, so our observations, where did the electrical current that you saw with your eyes start? Where was the starting location? Near the transformer. And Sam, can you describe a little the geometry there? They can't see it too well.
It goes inward and goes out like that.
So the distance of closest
Is at the bottom.
approach, the distance of this closest separation is down there, and that's where the spark started, right?
Yeah.
Okay, go ahead and show them so they can see that.
You want me to turn it on?
Yeah. So you see where it's starting? Okay, turned off. Okay, so it's starting down there. We're going to use Sam's quiz for this. Makes it easy, right? And then you'll enjoy it, actually.
I will.
Okay, so what's the separation at the closest point?
Like a centimeter.
1 centimeter. You guys already were told what the electric field breakdown strength in air is, right? Three million volts per meter is 30,000 volts per centimeter. If it's 1 centimeter separation, then what's approximately the voltage difference here? Somewhere around some tens of thousands, right? To get it going. Then once it gets going, what happens? It expands and it is rising. Why does it rise?
There's less resistance at the top.
Okay, one idea would be less resistance at the top. But let's think about it. As we get up here, this separation is bigger, right? So the resistance might actually get bigger if the area stayed the same for the arc going across there. So probably not that. But it's an idea to throw out, right? And consider. What's another reason it might go up? if we have charges moving, maybe there's some force associated with moving charges. And indeed, we will find that there is in the next few lectures with magnetic fields. Moving charges in magnetic fields have forces. However, hot air rises. Heat is being generated. And the arc is heating the air up pretty well there. So it's causing the air in the arc region to be hotter, lower density. The buoyant force of the colder air in the room pushes it up. Now we could test that, couldn't we? By turning the thing upside down and seeing which way it goes. Maybe it just likes to go to wider wire after it gets started. But do you want to do that or not?
Sure.
I'm not sure we can do it safely. Let's see how heavy this guy is. Yeah, you got that side, right?
Yeah.
Okay. Yeah, see now, I think I would be comfortable, but I'm not comfortable with you because you're, okay, put it back up here. Okay. We're gonna skip that one. I'm gonna assert that that would work, that if we turned it upside down, it would just go this direction. But I don't want Sam to get shocked. And
Not to say it can't possibly start from the top ever.
I'd have to bring the wires closer together. If I brought them to be the closest up here, closer than there, then yes, it would start up there. And you'll notice I haven't been touching the wires since you did it, right?
Yeah.
Because it makes heat. The current is flowing, and that resistivity there, right? Resistance, friction, is making heat. The wire's getting hot. And you know how you can brand cattle to know which farm or ranch they're from? We could do that with these wires. Not at this moment, but just after turning it on, it would work great for that.
Yeah.
Okay? So let's not do that. Now, let's turn it on and watch it again. So it's flopping around. It was flopping around. I have to use past tense now. I hear it. I hear it. You want to. Okay, it's flopping around as it goes up, and to your eye it looks like it's steady, doesn't it? Now let's prove that there's some energy delivered by lighting Sam's quiz on fire. Okay. And now, we didn't do it yet. I want to show something. Let's watch what happens here. Come on. This paper is not, oh, there we go. Okay, are we ready? Now, what do you see here?
Dots in like a wave.
Exactly like where the spark was going,
where
right?
the spark is, there's a wave of
You
dots.
ready? And I made a new set here, didn't I?
Yeah. Just like
So
two waves.
this is turning on and off. It's not steady state. It's turning on and off at about 120 times per second because this is 60 cycle electricity. And, oh, I chose a poor part to burn, didn't I? It starts with an M?
Yeah.
Okay, well, we'll work it out. Okay, so this is going on and off. The electric field gets big enough to cause a breakdown, and then it shuts down, and then it turns on again. So this is alternating on and off. It's not on all the time. Okay, Sam, have a seat. Thank you very much. Okay, let's, have you helped? Have you helped? Yeah, I know, I need a female. I just had a male. You've already helped. Have you helped? Ah, the eyes averted. Have you helped? Why don't you come on up and help now? See, you can look after a while the psychological. Have you helped? Okay, but one of these guys is not, is that right? This guy?
This guy right here.
Hi there.
Joyce.
Joyce?
Yeah.
Hi. I had an aunt named Joyce.
Oh, really?
Yeah, long ago. She passed away a long time ago, unfortunately. Okay, so Joyce,
Yes.
may you live a long and prosperous life.
Thank you.
Okay, and that's quite the shirt.
Yeah.
Whoa, what's that say?
I have no idea.
It looks like me. Okay, so, all right, so, yeah, show them the shirt.
Oh, it's a skull.
It's a school? Okay, all right. What's the school?
Huh?
What's the school?
Oh, it's a skull.
Oh, a skull. Oh, even worse. Okay, all right. So now let's work with these light bulbs, okay? So we're going to make some current flow. We're going to put the current, flow the current into a capacitor right here. Why don't you read what it tells them on the capacitor?
Mallory.
Mallory, okay.
Made in USA.
Made in USA. Some brand stuff, huh?
Yeah.
Does it say anything below that?
Type CG.
Right, keep going.
8,400
M,
MED.
M-E or M-F, do you think?
F. Or
M,
capital M.
I don't know. So we got a 8,400 M, possibly FD. What's that say?
75.
VDC. That's not Vista del Campo. VDC is volts DC. Volts DC. Positive, something 85C, max surge, 100 volt DC. Okay, so we got ourselves a capacitor, and when you read the outside of these things, it tells you about the physical values of the capacitor. Okay, let's turn on the power supply. Let's turn this guy on. Yeah, now let's turn that guy on. Okay. That was not exciting, was it?
Yeah.
Throw a switch. Go over there. Go to the other side with the switch. Just. Oh, I like that. Let's see. Go to the other side. Let's see what happens. That's good. Come on over here. What does this read?
It's going down.
It's going down. It was higher value. And what's the scale say on it?
Milliamperes.
Milliamperes. Milli is the first name. Amperes is the current. Amperes is what we use for total current, are the units, amps. So milliamps would be 1,000th of an amp. And this thing was up at about 100 milliamps to start. So it was charging, the circuit had 0.1 amps flowing in it. Now it has what?
0.
0. And what does it say for voltage? Oh, it's a little confusing now. We have two possibilities to read, right?
It's 100 on the red scale.
On the red scale, and that's what we're on, right? So it was charged, the capacitor was charged to 100 volts. Joyce charged it to 100 volts. And then the current slowly went to 0. The voltage is still trying to push at 100 volts at that capacitor, but because the charge is built up on the capacitor now to have enough charge there to make the electric field in the wire equal to 0, no further charge is pushed onto the capacitor. Stand right here and throw that switch over to the other. Just put it back to the first position, and then you want to see it again now, don't you? Ah, you saw the qualitative sense, and then you realized, uh-oh, now we can also do quantitative. Remember, it's not satisfying until you can apply a number to it. Let's charge her up again, Joyce. How many seconds did you get?
11.
Okay. And where, Joyce was sitting there. So can you provide her with some, does she make good notes?
I'm not sure. I'll have to see.
Okay, so the way you see is you get some notes from her and then you compare from over here too, right? So you get a chance to know, okay? How are we doing?
It's getting close to 0.
Getting close to 0, right? So that when the voltage could push really well, the current was quite high. And then as this more and more charge got stored in the capacitor, the voltage on the capacitor rose up and it opposes the flow of the charge, right? So it gradually got to where it's 0 now. And now are we ready? Now let's do a, you want to snap and do a countdown so they'll all be able to quantify?
Okay.
You ready? You do it. You do it.
2.
Was that enough? Yeah? Okay. All right. So even with a little adrenaline rush, you got within about 10% of the same for how long you saw it, right? You count a little faster when the
Yeah.
adrenaline's going, don't you? That's normal. I do that too. Time flies when you're having fun. Okay, now, that was this one. Shall we go to this guy? Let's charge it up. Go ahead. What we are seeing here to start with, the start of this lecture, I said capacitors store energy. And we calculated a half CV squared, and then hopefully got the C in the right place on one of those equations. So the half CV squared, and we are dissipating that energy by driving a current through a resistor, which heats up. And when it heats up, we get black body radiation coming out of it, and we see it, the visible light portion of it. So the current flows through a resistor, dissipating the energy which was stored in the capacitor. This ties all of the entire lecture together, doesn't it? In a wonderful way. It makes light. Okay. You ready?
Yeah.
Go for it.
Oh. Yeah.
I like that clock. Oh. Okay, we need to do it again, don't we?
Yeah.
Now, let's make a little qualitative observation. The bulb this time lasted about how long? 1 second versus the other one was 10, 15 seconds. Was this one brighter?
Yeah.
So, and this one was duller? Which bulb do you associate with? The brighter bulb, right? I think Joyce is the brighter bulb today then, okay? And we have now, let's go for that again. Go for it. Ah, that's interesting. Now, let's go charge it up. What's the voltage over here again?
100.
100 volts. What's the, go ahead, charge it. What's the maximum current is about?
125.
125 milliamps, she says, is the maximum current. And then it reduces. If we were to draw a graph of the current versus time, what would that look like?
Negative slope.
A negative, yeah, going down. Shall we do that? If we were to make a little graph of the charging current versus time, starts out at about 125 milliamps, and it goes gradually down like that with that kind of curve to it, and then it takes about how long to get out to here?
Maybe like 5 seconds.
5 seconds to charge, and then it keeps going a little closer, a little closer, a little closer, right? Okay. Now let's go ahead and now let's take a look at the light intensity coming out of the light bulb also. Go ahead. I'm seeing spots. I don't know about you guys, but I was looking right at it when she flipped it. So Was it very intense right at the start? And then the intensity decreased kind of exponentially, just like we've got for the charging of the capacitor. The discharging of the capacitor had an exponential also, didn't it? This was for charging. And this was current. The charging current, and we could make a graph of intensity of the light. Yes? What should I use for the symbol for intensity? What's the first letter of intensity? I. And didn't I just use an I over here for current? So I'm going to mess with your minds. I'm going to put I of the light intensity over here. And that one started out at some value and went down. This bulb says it's a 150 watt light bulb. What does that mean? 150 joules per second, and what that means is that's the power that's consumed by it. It is not the lumens that your eyeball can see. But if it's about as bright as a 150 watt light bulb when you look at it, doesn't that tell you it's using about 150 watts? So did we charge it again? Oh, please, please. Good idea. We're going to charge it again. You're going to compare the initial brightness with what you expect to see for a 150 watt light bulb. And you give me a rough idea then of what the initial power was. I'm running out of patience. I just don't have it. But it's still got more to go, doesn't it? Should we tell jokes or
Do you have any good ones?
do I have any? The ones I think are good, people usually, they don't like them so well. You know?
I think you should try it though.
Okay. Let's,
It's the
are we ready?
Yeah.
Go for it. How bright was it compared to a 150 watt light bulb? Close, but not quite, right? So would we say it's 100 watts? And it was for about 1 second. So how much energy was dissipated? 100 watts times 1 second is 100 joules. So the capacitor stored somewhere around 100 joules. Maybe it's 50 joules. You know, we could be off. Maybe it's even 25. We're just making rough guesses right now. Rough estimates, not guesses. Are you happy?
Yeah.
Joyce is happy. Okay, so thank you very much, Joyce. Good job. And will you gals make sure she has some good notes, please? Okay, so resistance, resistivity. Turn those guys off. We need to do power dissipation, but I think that may be in the next lecture. Yes?
How many watts was the smaller bulb?
How many watts was the smaller bulb? Well, on it, it says 15 watts on it, but it was a little on the dull side as well, right? So maybe it was 10 watts for 10 seconds, roughly. Now, what I've done, I've got this exponential decreasing curve, and I kind of took the first part and just pretended it was a rectangle in terms of area on that graph. I didn't do an integration with that diminishing. So I'm kind of overestimating the power by roughly a factor of 2, something like that. But it's somewhere around 50 joules, I suppose, and 100 joules is possible. And also it keeps going after we can't see it anymore. That just gets it cool enough that you don't see it radiating. Any other questions on the demo? Yes?
One both light bulbs were connected and the small light bulb was lit, were they both like connected in a series or something?
No, this place where you've got them just sitting here, it's a good question. You can't see it from there. It's just a holder for the spare bulb. It's not wired to anything at all, okay? So just to prove that, I'm holding the bulb, all right? This one will light up. You ready? Oh, I didn't wait long enough.
What's the capacitor made of?
What's the capacitor made of? The capacitor is typically made up of a very thin sheet of conductor like aluminum, very thin, like aluminum foil, and even thinner than the foil you buy at the market. And then the next aluminum foil sheet that's right near it is separated from it by a little sheet of typically mylar, some kind of insulator that does not conduct. And then it's rolled up. And you can see this guy, the shape looks like it could be rolled up. So that way the sheet doesn't occupy very much volume in real space, but you can have real close separation between the sheets to get high capacitance also. Okay, so now I'm holding this one over here, right? Okay, so it's just a storage place. Do you want me to prove it by doing the other way? You're good, huh? Okay. All right. Well, I guess that's it for today. Oh, I should say, today is Tuesday, right? I understood that there was an absence from one of the discussion sections last time. Look at the class webpage because there are 3 discussion locations. And if you happen to have somebody not show up by accident, go to one of the other 2. It should work fine. Or work as a group together. That should work fine also.